Today we will discuss about the Bose-Einstein distribution formula. In Bose-Einstein distribution, the particles are integral spin. The particles are indistinguishable. They are identical, and the particle in a state, there is no restriction how many particles will be in a particular state, and the wave function is symmetric wave function. Considering this item, we can derive the Bose-Einstein distribution formula as there are ni number of particles, and these are the particles, and gi number of states. So we can keep any particle in any state and large number of particles in a particular state. So to have the distribution, we keep the first state fixed, and other samples are randomly oriented. Then we have total number of objects is ni plus gi, that is the number of particles plus number of states, and the combination of the there is various combination to keeping the first one fixed, that is remaining particle objects are n plus gi minus 1 can be distributed in various ways. That is the number of distribution is this. The different type of distribution, this type of distribution, and the distribution among as the particles are indistinguishable, so distribution among the particle is meaningless, so we divide by n factorial, and the states are all are equivalent, and so the distribution among the states are equivalent. So for a particular ith particle, for a particular state, the number of distribution wi equals to this, and for w1 equals to n1, g1, n2, and for w2, for w3, and the total number of distribution would come as equals to w equals to product of, this is the term for product equals to I equals to 1 to n ni plus gi minus 1 by ni factorial gi minus 1 factorial. But when we are considering that the particle is large, number of states is large, actually the particle is large, then the ni plus gi is large enough compared to 1, and gi is also large compared to 1. So we can write it as in approximately or nearly as w equals to nearly equals to or product of I equals to 1 to n ni plus gi factorial by ni factorial gi factorial, and ln w equals to sum of ni plus gi ln ni plus gi minus ni plus gi minus summation ni ln ni minus summation ni minus summation gi ln gi minus summation gi. We are using the Stirling approximation formula, and we get that this should be and Ni minus Gi, and this will be minus Ni plus Gi, and this will be plus. So this one and these two will be cancelled out. So remaining terms are delta L W equals to delta L W equals to this. So this has to be maximized. This has to be under equilibrium condition. This will be maximum. So delta of this is equals to 0 for equilibrium condition. Then delta of this equals to how much? Delta of this equals to, this will come out as sum of the derivative of this equals to 1 by Ni plus J equals to 1 delta Ni plus, and the derivative of this, and this is constant, then delta Ni ln Ni plus Gi minus delta Ni ln Ni and minus summation delta Ni, and this will be derivative of this equals to 0. So this comes out as this two term cancels out and equals to delta Ni ln Ni plus Gi by Ni. And this has to be maximized under the condition using Lagrange underdevelopment multiplier that delta Ni into alpha equals to 0. Summation of delta Ni equals to, under the condition, and the condition is this, and another condition is Ei delta Ni equals to 0. This comes from the conservation of particle, and this comes from the non-interacting system of the non-interacting particle. So total energy of the system is constant, and using these two conditions, and this has to be maximized using the Lagrange undetermined multiplier, we can write it as Ni plus Gi by Ni minus alpha minus beta Ei into delta Ni summation equals to 0. So this has to be delta Ni is not equals to 0, so this is equals to 0. That means we get Ni plus Gi by Ni equals to alpha plus beta. Here there was a ln equals to alpha plus beta Ei. So Ni plus Gi equals to Ni plus Gi by Ni equals to e to the power alpha plus beta Ei, and we can write as 1 plus Gi by Ni equals to e to the power alpha plus beta Ei, and so Gi by Ni equals to e to the power alpha plus beta Ei minus 1, and this we can write Ni by Gi equals to 1 by e to the power alpha plus beta Ei minus 1. This is the distribution from a number of particle per energy state, and this distribution is the B.E. distribution formula, and B.E. distribution formula comes out as 1 by e to the alpha plus beta Ei minus 1. And now we have to find out the constant alpha and beta. Now ln W B.E. Bose-Einstein distribution equals to, where we get this sum of Ni plus Gi ln Ni plus Gi minus Ni ln Gi minus Gi ln Gi. Yes, the entropy in Bose-Einstein statistics equals to K ln B. In K into this will come as this. And delta change of delta B equals to change of entropy equals to K change of this equals to delta Ni, and this equals to, this gives the 2 term, and this gives the this 2 term, and this is derivative of this equals to 0, and this 2 term cancels out. So we get delta B equals to delta S equals to K into delta Ni sum ln 1 plus Gi by Ni, which is equals to delta S equals to K delta Ni e to the power ln of e to the power alpha plus beta ei, that equals to K sum delta Ni to alpha plus beta ei, that is equals to K sum alpha delta Ni plus beta sum beta ei delta Ni. This is equals to K sum alpha delta Ni plus beta into ei delta Ni equals to U. So del S, so from the thermodynamics we know that del S del U at constant V equals to 1 by T equals to del S del U equals to 1 equals to beta. So this equals to, there is a term K beta, there is a K, so K beta. So beta equals to 1 by Kt, and alpha is generally taken as minus mu by Kt. So we get that Ni equals to Gi by e to the power Ei minus mu by Kt plus minus 1. In epsilon MEDE equals to GEDE by e to the power E minus mu by Kt minus 1. So we get the BE distribution formula like this.